Samarium-neodymium dating, Lincoln dating. Samarium-neodymium dating is a radiometric dating method useful for determining the ages of rocks and meteorites based on the radioactive decay of a long-lived samarium isotope 147 Sm to a radiogenic neodymium isotope 143 Nd. Neodymium isotope ratios together with samarium-neodymium ratios are used to provide information on age information and the source of igneous melts. It is sometimes assumed that at the moment when crustal material is formed from the mantle, the neodymium isotope ratio depends only on the time when this event occurred, but thereafter it evolves in a way that depends on the new ratio of samarium to neodymium in the crustal material, which will be different from the ratio in the mantle material. Samarium-neodymium dating allows us to determine when the crustal material was formed. The usefulness of SM&D dating stems from the fact that these two elements are rare earth elements and are thus, theoretically, not particularly susceptible to partitioning during sedimentation and diagenesis. Fractional crystallization of felsic minerals changes the SM/ND ratio of the resultant materials. This in turn influences the rate at which the 143 Nd/144 Nd ratio increases due to production of radiogenic 143 Nd. In many cases, SM&D and RBS or isotope data are used together. SM&D radiometric dating. SM&D geochemistry. The concentration of SM&D in silicate minerals increase with the order in which they crystallize from a magma according to Bowen's reaction series. Samarium is accommodated more easily into mafic minerals, so a mafic rock which crystallizes mafic minerals will concentrate neodymium in the melt phase relative to samarium. Thus, as a melt undergoes fractional crystallization from a mafic to a more felsic composition, the abundance of Sm and Nd changes, as does the ratio between Sm and Nd. Thus, ultramafic rocks have high Sm and low Nd and therefore high Sm/Nd ratios. Felsic rocks have low concentrations of Sm and high Nd and therefore low Sm/Nd ratios. For example, cometite has 1.14 parts per million ppm Sm and 3.59 pPa. The importance of this process is apparent in modeling the age of continental crust formation. The CHUR model. Through the analysis of isotopic compositions of neodymium, DePaolo and Wasserberg 1976 discovered that terrestrial igneous rocks at the time of their formation from melts closely followed the chondritic uniform reservoir or chondritic unifractionated reservoir. 144 Nd ratio increased with time in chondrites. Chondritic meteorites are thought to represent the earliest unsorted material that formed in the solar system before planets formed. They have relatively homogeneous trace element signatures, and therefore their isotopic evolution can model the evolution of the whole solar system and of the bulk Earth. After plotting the ages and initial 143 Nd/144 Nd ratios of terrestrial igneous rocks on a Nd evolution vs. time diagram, DePaolo and Wasserberg determined that Archean rocks had initial Nd isotope ratios very similar. Epsilon notation. Nd model ages. The depleted-mantle model. Despite the good fit of Archean plutons to the CHUR Nd isotope evolution line, DePaolo and Wasserberg 1976 observed that the majority of young oceanic volcanics, mid-ocean ridge basalts, and island arc basalts lay +7 to +12 units above the CHUR line. See figure. This led to the realization that Archean continental igneous rocks that plotted within the error of the CHUR line could instead lie on a depleted mantle evolution line characterized by increasing Sm/Nd and 1Ho. To further analyze this gap between the Archean CHUR data and the young volcanic samples, a study was conducted on the Proterozoic metamorphic basement of the Colorado Front Ranges, the Idaho Springs Formation. The initial 143 Nd/144 Nd ratios of the samples analyzed are plotted on an E&D versus time diagram shown in the figure. DePaolo 1981 fitted a quadratic curve to the Idaho Springs and average E and D for the modern oceanic island arc data, thus representing the neodymium isotope evolution of a depleted reservoir. The composition of the depleted reservoir relative to the CHUR evolution line at time t is given by the equation E and dt equals 0.25 T23 T plus 8.5. SM&D model ages calculated using this curve are denoted as TDM ages. DePaolo 1981 argued that these TDM model ages would yield a more accurate age for crustal formation ages than CHUR model ages. For example, an anomalously low CHUR model age of 0.8 Gi from McCulloch and Wasserberg's Grenville composite was revised to a TDM age of 1.3 Gi, typical for references